Okay. Hello, everyone. Today, we will be talking about a new unit, which is the wave and vibrations. So we will talk about a wave and vibrations. Okay, so and then in this unit and next unit, we mostly talk about the application of the sound wave and also light waves. Okay, which is going to be the next unit. Good. What is the vibration? A vibration is a wiggle in time. What does it mean exactly? So when you have a motion, okay, or a periodic motion, so it means that the object is moving a same pathway in a period of time. It can be 1 second, it can be 10 seconds, it can be less than 1 second. So the same motion at a specific time. So we call it vibration. So what is important here? The motion of the particle. It means that the position of the particle and the time. Let's say I am moving my hand up and down 20 centimeter. Good? 20 centimeter up and down. So what is this motion? This is a periodic motion in a specific time. How long does it take my hand to go up and down? Let's say 1 second. So I can say I am completing this one motion, up and down motion, in 1 second. So this is called vibration. So, and we show the vibration with wave. We analyze the vibration, any motion which has a wiggle in time and position with wave. A wave is a wiggle in both time and space. So what kind of motion we can explain about this? Okay, so one is sound, good. The other one is light. We will talk later about how the sound is created. How the sound is created, let's say, see, mechanical force exerted on an object, yes, exerting on an object. The molecules inside the object start, vibrating, okay? When you are hitting this object, what exactly happened? You are exerting force. By exerting force, all molecules and atoms inside this solid object will start vibrating. You cannot see this vibration, but it is being vibrated. Good? And this vibration create a sound wave. So why we call it wave? Okay, because there is a vibration. Vibration in time and position. We create the sound wave, and then the sound wave travel through the medium. What is the medium? Is the air. That's why you can hear this sound. We will be talk about this more in the next chapter, okay? But I just wanted to know that, when we are talking about the wave, what the wave means. Okay, we have a sound wave and light wave. How we can create the sound wave? By exerting a mechanical force on an object, the atoms and molecules on the object start vibrating. Okay, that's how it's create the sound wave. And then light. Light is the vibration of the electric and magnetic field. What does it mean? So let's say we have a charged particle, and this charged particle has a negative charge or positive charge. When it is not moving, it does have just the electric field. We have a positive charge, it does have an electric field. And when these charges start wiggling or vibrating, not only does have electric field but also have a magnetic field as well. Any object which does have a moving electric and magnetic field create electromagnetism wave. Again, with more details, we will talk next unit about the light. Okay, just letting you know that we assume that the light is acting like a wave. Why? Because where there is a charged particle is vibrating up and down. These vibration of the charged particle create a light wave. Make sense? So when we are talking about the wave, it means that there is a vibration. Something is vibrating. Light, vibration of the charged particle, which create the moving electric field and magnetic field. Sound wave, vibration of molecules and atoms of the sound source. Let's say this table is sound source. I am exerting a mechanical force to this table. Table receive this force. All molecules and atoms start vibrating, and then this vibration create the sound wave. Okay. So we are talking, this unit, okay, about more about the the wave. Then in next unit, when we are talking about the wave, we will be talking about more particle, characteristic of the light wave. Good? So, but now we know what is the wave. Again, period. What does it mean? If this vibration and motion is happening in a specific time, you remember I said a specific time? This time is called period. Let's say we have these pendulum. Good. These pendulum does wiggling in a time and a space. Yes? Okay. So one complete motion, one complete through and one complete back and forth motion is called the time that it takes to complete one motion is called, okay. And we can have different periodic motion. So let's say you remember we talked about the car when it's moving through the circular pathway. Yes, let's say we have a a particle, and this particle starts its motion from here, and then it takes, let's say, t second to reach to exactly to its starting point. This time it's called period. So circular motion is an example of a periodic motion. Okay. Okay, wave description. We would like to analyze a motion, a periodic motion with a wave, but we need to know some characteristic of the wave. So, what is the wave? So, wave is like a sine and cosine curve. As you can see here, okay, these sine and cosine wave, okay, is a waveform, okay, which is kind of explain a simple harmonic motion. So as you can see here, there is a spring and the object is attached to this spring. Okay, let me just bring it a little. There you go. Now you can see. What you can do if you would like to create a wave to see how the wave is going to look like. Let's say we have a paper and this is, this box, rectangular box here, this rectangular box here is, let's say it is a paper. And you just start, moving this paper to the right. But what you do first, you attach a pencil to the end of this spring, which there is a hanging weight, yes? And then this spring start moving up and down. While this spring start moving up and down and you are pulling or pushing this paper, you will see that these sine and cosine curve will be created. So these, in mathematics, we just show this like a sine and cosine function. Again, you don't need to know about the function, okay? So, but you need to know that when we have a periodic motion, the best function to describe this motion is the sine and cosine function, or the sine and cosine wave. Good? So, and as you can see here, let's say this is our wave. Good? So we have wavelength, amplitude. What is the wavelength and amplitude? As you can see here, there are two peak, yes, and two min, two max and two min. The distance between any same point on the wave, so let's say this is a max, this is a max, the distance between these two in the wave is called the wavelength. So it can be from here to here. Again, it is a wavelength. Good? So it can be any point, any same consecutive point, okay? So it's going to be the wavelength. Good? So what is the wavelength? The distance between the two same point on the wave is called wavelength. So what is the amplitude? The amplitude, as you can see, you see there is a dash line. The dash line is the point when we have an equilibrium. Good? Or in the half, in the middle of the pathway. Yes? The point in the middle of the pathway, which we just show with the dash line. So the amplitude is going to be the distance from a max to this dash point, okay? So it's going to be the amplitude. So again here, the mean and this dash point is going to be amplitude. So let me just show with this. Again here, this is going to be amplitude. And then from here to here, it will call amplitude as well. Good? So we have a wave. So we define two things, wavelength and amplitude. The wavelength is the distance between two same point on the wave. So, and the amplitude is the distance from the midpoint to the top or bottom. So we will define a frequency. What is the frequency? Frequency is the number of vibration per unit time. So let's say, I have a particle, yes, and this particle moving up and down. Good. The period, or sorry, the frequency is the number of vibration. How many vibration I have? Okay, I count the number of vibration, good, divided by the total time. How many time it takes, okay, let's say I have my recorded time recorded, I click the start, and then I start counting the vibration. In 10 seconds, you just count, let's say 20 vibration. So the number of vibration over the total time is gonna be the frequency. So if I want to explain it, so frequency, so frequency, we just show it with F, is gonna be number of vibration over time. And the unit of the frequency is hertz, or 1 per second. Okay, the number of vibration, it means that the number of vibration, okay, it doesn't have any unit. The unit of the time is second. So let's say we have a particle, and this particle is moving through this circular pathway. Okay, so and then it's completing this circle, one vibration, the time it takes to start its position from the starting point, and it reach to exactly to the same point. Let's say it takes 1 second. Good. So how we can calculate the frequency? What was the number of vibration? One vibration, yes? One vibration over how many seconds? 1 second. So what is going to be the frequency of this moving particle? Is going to be 1 hertz. Let's say if it's complete one complete motion in 10 seconds. Good. What would be the frequency now? 1 divided by 10 seconds is going to be 0.1 hertz. What this 1 hertz means? It means that one complete vibration happened in 1 second. 0.1 hertz, you can say like this, okay? So you can say one vibration completed in 0.1 second. Yes? Okay, sorry, in 10 seconds. Good? Yep. That's why we call it frequency. Okay, so frequency is the number of vibration over time. So one complete vibration over time, okay, over period time is going to be the, so we can rewrite this equation like this. Let me just use another color. I can say frequency is 1 over t. What is the t? Period time. How long does it take to complete one vibration? Yes? You know, instead of number of vibration, good, I just plug 1. And what is the time when you complete one motion? You are completing in the one time period. Okay? That's why instead of time, I just place t, period time. If you already have a period time, you can plug into this formula F equal 1 over t and calculate the frequency. Okay? But if you have the number of vibration over time, you can plug in the second equation, okay, to calculate the frequency. Make sense? What is the difference between these? Okay, they are exactly the same equations. Good? But the principal equation is this, okay? Frequency is the number of vibration in time. I know that when we complete one motion, This time is called a period time. Yes? So that's why instead of number of vibration, I just plug one, and instead of time, I just put capital T, which is the period. Good. So you can calculate the frequency. And what is the frequency unit? Is going to be hertz or 1/second. So yes, we just discussed about the period. So we know the frequency and how the time and frequency, how the period and frequency are related to each other. What was the equation? How the frequency and the time are related to each other? They are inversely related to each other. The bigger period time, the frequency is going to be small, and it makes sense because it takes more time to complete one motion. Good? The smaller time period will give us high frequency. So the frequency and the time period, they are inversely related to each other. Yes, and then as you can see, period is equal 1/frequency, or frequency is equal 1/t, or t is equal 1/f. They are both same formula. Time is equal 1/frequency, or frequency is equal 1/time. Okay? So wave motion. Wave motion can be seen as a rhythmic disturbance in a medium where every portion of the medium is impacted as the disturbance follows along the medium, and then it returns to its normal. So you remember I talked about the sound wave, and I said that the sound wave is created by mechanical force, and the reason that you are hearing this sound wave because it's traveling and reaching to your eardrum. So what does it mean? How is traveling? Air is traveling through the medium. We have air. What is the air? The air is full of oxygen, hydrogen molecules and atoms. Good. The sound wave is created, transferred, and the air is transferring. These molecules are transferring this sound wave to your eardrum. That's why you can hear the sound wave. Good. So any wave need medium to travel. The only wave that doesn't need medium to travel is good. We have a sound wave and the light wave. The sound wave definitely need a medium to be transferred. And this medium is the atmosphere, okay? So air. So I'm talking. So the sound wave is created. The reason that you can hear because this sound wave is being transferred to your eardrum through this air. If there was no air or medium or atmosphere inside the class, so you would not be able to hear my sound. But again, the only wave that doesn't need medium to travel is light. Okay, so we are talking about wave is traveling. You remember we were talking about the particle. The particle was moving with this velocity. Calculate the distance travel. Yes? So right now we have a wave, or which here is a sound wave, and this sound wave is traveling. Definitely the sound will have a velocity. We call it a wave speed. Okay, so wave speed is gonna be frequency multiplied by time. There are different ways that you can explain or calculate the wavelengths. Okay, so what was the velocity's formula in the one-dimensional motion? It was distance over what? Time. Yes? Distance over time. So you remember we said that this is a wave, yes? Good. And I said that the distance between these 2 points in the peak part of the wave is wavelength, yes? And what are these 2 points? Let's say, the spring is moving up and down, yes? When the spring complete one motion, one back and forth motion, it takes t second from here to here. Yes, we call it t period time. Yep. Okay. Here, what is the distance between these 2 points? We call it lambda. What is the time that this point reach to the second point? Is a period time. Good. So lambda over t is going to be the wavelength. We already know that the wavelength or the frequency is 1 over t. Okay? So lambda divided by t, instead of 1 over t, we can just put a frequency. It's going to be lambda times frequency. So you need to know all those formula. The wavelength the wave velocity is distance over time. You can say distance is the lambda and the time is a period time. Okay? So it's going to be lambda wavelength over a period time or equal to, because we already know that the frequency is 1 over t, it's going to be lambda time f. What is the unit of the velocity? Meter per second. It doesn't matter is a wave or is a particle, is a projectile motion, the velocity of the wave, particle, or any motion, or wave is the periodic motion. Okay, so the velocity of wave is going to be meter per second. So we have two different forms of waves. The first one is a transverse wave. You see here, what is the transverse wave? Let's say we have a rope. One end of the rope is attached to the wall. The other end is in your hand. What you do, you just move your hand up and down. Up and down. Good? When you move your hand up and down, what exactly, is a periodic motion, yes? Your hand is doing a periodic motion, and this periodic motion will be transferred to the rope, and the rope will have a periodic motion. How we can explain this periodic motion? With the wave. See, the wave will be created on the rope. So in which direction the rope is moving? The rope is moving up and down, yes? But the wave is traveling forward, okay? 90 degree. The wave, again, rope, which is the medium, okay, is moving up and down. But the wave is created, the wave is traveling, okay, horizontally. Good. Your hand and the rope is moving up and down vertically. but the wave is traveling horizontally. This wave is called transverse wave. Okay, if we want to explain it, okay, motion of the medium is transverse or 90-degree to the direction of the wave. What is the medium? Rope, yes? The rope is moving up and down. But what is the wave direction? Horizontally. When there is a 90-degree angle between the medium motion and the wave motion, we call these wave transverse waves. Rope, one motion. Okay, it's the transverse motion. Good? Okay. The other form of wave is called longitudinal wave. Good? Let's say instead of rope, okay, you have a spring. Good? And instead of moving a spring up and down, okay, you just push and pull this spring. What exactly happened? A spring goes back and forth, yes? See here, instead of, moving up and down, you just push or pull, yes? What happened? So the medium, which is the spring, yes, it's moving horizontally again, back and forth horizontally. There is a wave created. You see the compression and the rarefaction here? This is where the compression happened. This is where the rarefaction happened. Okay, the distance between these two compression is called wavelength. Okay, let me just show here. This is a compression. This is another compression. We call this distance a one wavelength. So you see here, A is gonna be longitudinal wave because the medium and the wave are moving at the same direction. Make sense? But the B is a longitudinal, again like a rope. No difference, yep. So the A, which is this one, is the longitudinal, but the bottom one is transverse wave. Okay? So now we know what is the difference between the longitudinal wave and transverse. Transverse, when the medium and wave are perpendicular, the motion of the medium and the wave are perpendicular is a transverse wave. Longitudinal, when the medium and the wave are moving at the same or opposite direction. Good? Okay. Okay. So far we have talked about one source of sound wave, or let's say mechanical wave. If we have more than one source of sound, let's say you are sitting on the other side of the class, okay, and you hitting the table, and I hit the table as well at the same time. Good. Now we will have two sound source, that black table and my table. Good. We have two sound wave. If all of us start hitting the table, okay, we will have let's say how many we are in the class. Okay, let's say we have 15 students in the class. We will have 15 sound waves or sound source. Okay, explain to me which sound wave you will hear. from 15 sound source, okay, which one you will hear? All of them? And how you can distinguish between all these? Can you distinguish the frequency, the time? So let's assume we are, okay, these are two important things because let's say I just hit, okay, you just hit 1 millisecond later, okay, at different time. So, and then you are telling that, okay, I hit more, exert more force, okay, you hit small force, okay, so the frequency will be different. Okay, time and frequency is important. But assume that we are hitting at the same time with the same force. And the table, all table are the same. Good? So it means that we are creating a same frequency and hitting at the same time. Okay, creating sound wave at the same time. So what happened? And you cannot distinguish between these frequencies. What happened? What sound wave you will hear? You will hear the resultant sound wave. These waves, they interfere. Your sound wave, my sound wave, your sound wave, okay, reach to one point at the class, okay, at any point, because the sound wave is traveling three-dimensionally. When I create, okay, sound wave, this sound wave, okay, goes in all 360-degree. Your sound wave goes at 360-degree. When I am creating sound wave is reaching to you, he is creating sound wave reaching to you at the point that is hitting, reaching to your, eardrum. They interfere. They combine. Okay, good. But we have two forms of interference: constructive interference and destructive interference. What is the constructive interference? Let's say these sound wave that we created, they reach, at the same time and the same position, okay, at this situation, the crest of the two wave, yes, they reach at the same point, okay, and the trough are at the same point. What exactly happened when we add these two waves? Definitely, if this is the amplitude A and this is the amplitude A, the resultant is going to be 2A. Yep. If this is again A, this is A, this is going to be 2A. So what we call this is a constructive interference. But let's say these sound waves that we create at the point that they are interfere, the crest of one is meeting the trough of the other sound wave. Yes? So this is the A, this is negative A. Yes? A plus negative A is going to be 0. This is negative A and this is A. What happened when you add or when these two sound wave or the wave interfere? They cancel each other. It means that you won't hear anything. Okay? So let's say there are two speakers. You are in a big salon, okay? So, or, open space, open area, and there are two, speakers, and these speakers are creating a sound wave. In that, salon, okay, or the open space area, there are some point or some places that you won't hear anything. What are those points? Those points are the point that the destructive interference happen. The sound wave, they cancel each other. But there are some point, okay, or some position on those area that you hear the high pitch frequency. What happened when there is a con those are the point when the constructive interference happen. Good. So we will have interference. What is the interference? It is the superposition law, and by superposition law you can add two waves, and when they are at the same phase, we call these two sound wave. Okay, so these two sound wave, we just say they are in at the same phase. When they are in the same phase, when we are adding these two or using the interference or the superposition law or principle, they add each other. So same, but these two, they are there is a phase difference. Okay, phase difference between these two, and the phase difference is a 180-degree phase difference. Okay, when you add them, okay, they completely cancel each other. Okay, what time? So let's do. Okay, so standing waves. So we talked about the interference of the wave when we have more than two wave source. It can be sound source or it can be light source. Okay, so the interference or the superposition law, it's we can use it for light source and sound source. Good. So and let's talk about the standing wave. Okay, so in the standing wave, we will try to use the interference of the wave and to be able to explain the standing wave. For instance, here you see this girl. So there is a rope, and one end of the rope is attached to the wall. Good. Is not moving. This is attached to the wall. The other end is in the hand of this girl. Good. And this girl is trying to move the rope up and down. What exactly happened? The wave is created, transferred through the rope. Yes? It is a transverse wave or longitudinal wave. Transverse wave. Yes? And this wave is reached to the wall. What exactly happened when it reached to the wall? The wave is traveling, reached to the block. The block doesn't move. You remember the Newton's third law of motion? When you're exerting force on the object exerts exactly the same force back. The wave is reaching, the point of the wave is reaching to the wall. Okay, the wall doesn't let it to pass through the wall. Okay, what exactly happened? The wall will reflect it back. So see here, we have incident wave, okay? And the dashed line one is the reflected wave. So what does it mean? We have two sources, two wave sources. One, the wave is reaching to the wall. The other one is the wave is created by the wall, which reflected back. Yes? We have two waves. When we have more than two waves, we can use the superposition law and add these two waves or interference. So definitely we will have a constructive or destructive interference. Okay? Combination of these two. See here? So incident wave reached to the wall, a dashed line is the reflected one. They are in the same phase and they add each other. Good. So let's say incident wave and the dashed line is the reflected wave. They are out of phase, are different phase. They cancel each other. Good. When they add each other, we will have antinode. So you remember we said that, they add their amplitude. If the amplitude is 1 and the reflected one is is A and A, okay, the new one is going to be 2A. Good. That point which adding the amplitude, okay, which will be here, we call these antinodes. The point that they cancel each other, see, is going to be node. Good. So here, as you can see, we will have one node, okay, two antinode, okay, when there is reflected back. So the resultant of these waves, when you are creating the standing wave, the resultant of this wave is going to be A, B, C, or D, E, F. It depends on the frequency. It depends on what frequency this girl is moving the rope up and down. So if the interference of the incident wave and reflected wave become these, we call these first harmonic or fundamental harmonic. This one, if you double the frequency, let's say the frequency for this one is the F0, we call it the fundamental frequency. If you double the frequency, if you ask the girl, okay, double the frequency, what exactly happened? Instead of first harmonic, we will have second harmonic. So we will see two loops, yes? If you ask this girl, okay, to triple the fundamental frequency, which create the first harmonic, you will have a third harmonic. Okay, let's analyze this a little more. Okay. So again, this girl, okay, there was a girl here and there was a wall and then there is a rope, yes? Good. And the length of the rope is L. L is the length of rope. And what happened? This girl start pulling, this rope up and down. We will have a superposition law, we will have constructive and destructive, yes, interference. Based on the frequency, let's say if we start with the first fundamental frequency, okay, what wave it will be created? Okay, this wave will be created. Good. So we call this F1. F1 is going to be F0, or we call it first fundamental frequency, fundamental frequency. Okay. So what is the wavelength here? If we say that this is the L, yes, the length of the rope is L, what is the wavelength? You remember what was the wavelength? Good. The distance from this point to this point is 1 wavelength, yes? Or let's say the distance from these two same point, yes, is going to be the wavelengths. Good. So see here, if this wave was traveling, it would travel like this. Let me just, okay. See this? It is a complete wavelength. Okay, one complete wavelength. But this one is a half a wavelength. Half a wavelength. Okay, so I can say the lambda for the fundamental frequency, so the lambda, I call it lambda 1 for the fundamental frequency is going to be lambda over 2. What is this lambda over 2? The lambda over 2 is the length of the rope, yes? From here to here is the rope length. Okay, so the lambda over 2 is going to be L. Good? So, second, I said if I double the frequency, we will have second harmonic. Yes? So, what happened in the second harmonic? So, again, we will have the same thing. Okay, this is a starting point. Good? So what is the frequency? What happened to the frequency? The frequency is doubled, yes? F2 is going to be 2F1 or let's say 2F0. Okay? So what happened to the lambda then? What is the lambda? The lambda 2 is going to be, see, each one of these is a half a lambda, yes? Half a lambda, half a lambda. Okay, half a lambda plus half a lambda is going to be what? Just lambda. Good? Half a lambda plus half a lambda is going to be lambda. What is the lambda? The lambda and this lambda 2 is going to be exactly the length of the string. So if you have the length of the string, you can calculate the lambda, yes? Let's say the L is 10 meter. What is the lambda here? 20 meter, yep. L was 10. What is the lambda here? 10 meter. Good? So move on to the oh, third harmonic. Okay, if I triple the frequency, what happened here? The lambda, the wavelength, okay, here is going to be good. So what is the frequency? F3 is going to be 3F0. The frequency for the third harmonic, okay. F3, it means that the frequency for the third harmonic, okay? F3, it means that the frequency for the third harmonic definitely is triple the fundamental frequency. And what is the lambda 3? How many lambda we have? We have 3 half a lambda, yes? So half a lambda plus half a lambda plus half a lambda. So it's going to be 3 half a lambda. And these 3 half a lambda should be equal to L. Yep. And L lambda is going to be 2L over 3. Okay? 2L over 3. And L was how many meter? 10 meter. Good? L was 10 meter. Okay, so you can, if you have problems seeing this, okay, you can open your laptop. Okay, click this code. Okay, so I think I kind of explained this. Okay, so you can open your laptop, go to this website, classpoint.app, and put this class code. Okay, you would be able to just, see the entire screen in your cell phone, in your laptop. Okay. Good? Okay. If you want to do, okay, do one more time. Okay, so I think laptop is better. Okay, so you can. Yeah, I think you already know that, okay, because last time I kind of explained that. Good. So you can use even your laptop. Let's say, go to this website, classpoint.app. So class code is going to be Phys120. Good. So you would be able to see the PowerPoint in your laptop or your cell phone. If you have problem just seeing it, okay? I know that, we should have a bigger screen, but unfortunately. Okay? So again, when you are joining to the class, you don't need to put your real name. Good? Put your name, I don't know, Y1, whatever, Z2. Okay, so again here, if I calculate this lambda, if I have the length of the string, which is 10 meter, the lambda or the wavelength for the third harmonic is going to be, if you just plug the L10 here, it's going to be 20 over 3. Almost 6 point something, okay? Let's do the fourth harmonic. If I do the fourth harmonic, okay, so the frequency change to 4 time. If you change the frequency to 4 time, so the length of the string, 1, 2, 3, 4. Good. We will have 4 loop, and each loop is half a lambda, half a lambda, half a lambda, and half a lambda. What was the frequency for the fourth harmonic? 4f0. Yes. 4 time. If you have the frequency for the first fundamental harmonic, if you quadruple that, okay, you would be able to create this wavelength, standing wave, with the 4 loop. We will do this experiment in the class, okay, next week. So, and what is the lambda? The lambda 4 is going to be how many lambda we have? Half a lambda, 4 half a lambda. Yes, if you add these 4 half a lambda plus half a lambda plus half a lambda plus half a lambda is going to be 4 half a lambda, which is going to be 2 lambda, and these 2 lambda should be equal to the length of the string. Yes. So L. So what is the lambda here again? Is going to be, because this is the equation, lambda is going to be L over 2. What was the L? 10 meter. Good. So what is the lambda here? 10 divided by 2 is going to be 5. You can do the same thing for the fifth harmonic, sixth harmonic, 7 harmonic. Okay, do the same calculation. So in the fifth harmonic, how many lambda we will have? How many half a lambda we will have in the fifth harmonic? We have 5 half a lambda. Yes. So in the fifth harmonic, so frequency is going to be 5f0. So we will have 1, 2, 3, 4, 5. Good. Half a lambda, half a lambda, half a lambda, half a lambda, and half a lambda. So how many half a lambda we have? We have 5 half a lambda, which is going to be equal to the length of the string. If since we already have L, how we can calculate the lambda? Okay, so just divide both sides by 5 over 2. Yes, 5 over 2, 5 over 2. Lambda is going to be what? 2L over 5. Okay. What is the L again? 20. L is 10. 2 times 10 is going to be 20. 20 divided by 5 is going to be 4 meters. So the lambda is going to be 4 meters. So how many node and how many anti-node I have here? Can you explain that? These are the anti-node, yes? when we have a constructive destructive interference. You remember from this? You remember node? Here is node, yes? Okay. So here is node. Here is node, node, and we have antinode. In the first harmonic, how many nodes we have? We have two nodes, one antinode. So, and in the second harmonic, how many nodes we have? One, two, three. How many antinodes? Two. Okay. So let's back to this slide. In the fifth harmonic, how many nodes we have? 3, 4, 5, 6. Yes, 6 nodes. Yes. And how many antinodes? -1. Okay. So it's going to be 1, 2, 3, 4, 5. Yes. 5 is going to be antinode. Okay. This is a standing wave. Good. And how the standing wave is created? The standing wave is created by interference of the reflected wave. So let's say you have a rope. You start, vibrating the rope up and down. You create the wave. The wave reaches to the wall. The wall doesn't let the wave pass. Okay, it's reflected back. The interference of the incident wave and the reflected one create the standing wave. And the standing wave can be in its first harmonic or fundamental harmonic. It can be in the second harmonic, third harmonic, fourth harmonic, and fifth harmonic. And it's all depend on the frequency. What is your frequency? If you are creating a small frequency, it is more likely to create the first harmonic of the standing wave. If you find the first harmonic, let's say you would be able to measure your fundamental frequency. Good. You create the first harmonic. If you double this frequency, definitely you will create two loop or the second harmonic. If you triple this fundamental frequency, you will create the third harmonic. We will do this experiment, next week. Okay, which is a very fun activity. Good. Let's move on to the next slide. Okay. Doppler effects. What is the Doppler effect? So Doppler effect, we just analyze it conceptually here, but it does have a calculation. But what is the Doppler effect? Let's say we have a sound source. Good. And a person who is hearing a sound wave created by this sound source. Both are stationary. Okay? Both are stationary. So you will hear a same frequency always. Good? If you measure the frequency of the sound that you hear, is going to be same. But what happened? What happened if you move toward to the sound wave, sound source? It's louder. Gets louder. Louder means high frequency. Yes? Louder, you hear the louder sound. So the frequency that you are hearing is bigger than the time when you were stationary, because you are moving toward to the sound source. Yes, and it is more likely that you hear more sound or louder sound. So what exactly happening? The frequency increase. What if you move away from the sound source? Gets quiet. Okay, so frequency decrease. Yes. What if you stay stationary and the sound source moves toward you? Louder. What if you are stationary and the sound source moving away from you? Quieter. What if if sound source and the person move toward to each other? Louder, even bigger than when you are moving toward, or the sound source is moving toward you. Okay, Frequency is going to be bigger. Good? So this is called the Doppler effect. Frequency is changing. Frequency is related to the wavelengths, okay? So when the frequency is changing, it means that the wavelength is changing. Good? And the Doppler effect is, and this is correct for the light source as well. So we can, because we use the Doppler effect and we analyze the stars' motions, galaxies' motions. Why? How? Because stars release or create the electromagnetism wave. It can be visible light, okay, or it can be X-ray, gamma ray, okay, infrared, whatever. Those waves, when they are reaching toward to the Earth, sometimes they blue shifted or red shifted. What does it mean? It means that this light source is moving toward to the Earth or moving away from the Earth. By measuring those wavelengths, we would be able to calculate how fast, okay, we are moving away from the star or galaxy or moving toward to the galaxy or a star. Good? This is a Doppler effect. So that's why you hear a blue shifted or red shifted. So not only the frequency change, see frequency, okay, the frequency is inversely related to the wavelengths. If I am telling that when the sound source is moving toward to me and I hear the higher frequency, the wavelength is gonna be bigger. Sorry, it's smaller. Okay, because the frequency is increased. Yes, the frequency when it's the sound source is moving toward you is increasing, but the wavelength decreasing. That's why we said that the blue shift happened here. When the wavelengths increase, okay, we will have a red shift. Okay. So I think you know the concept, okay? So what exactly the Doppler effect means, okay? We use it for light and sound, okay? So bow waves. So let's say the sound source, the sound has velocity. The sound wave does have velocity, and its velocity is 340 something meter per second. The sound source velocity cannot be bigger than this, okay? The atmosphere, it affects the sound source, but it affects not too much, okay? So if let's say you are in the environment, okay, in the air temperature with 25 degree and the sound source is traveling, the velocity of the sound source is 340 meter per second. If see this line, a circular line, it kind of showing the wave, how the wave distributed, the wavelength is distributed through the space. Good. So why are we showing the circular? Because we know that the wave is traveling three-dimensional. So 360 degree, yes? In all dimensions. So let's say you have a sphere, you connect the line, okay, from the surface of the sphere, you connect any point toward to the center. You will see the lines, yes? Good. So these are those lines. So, and you see these lines here, okay? So it's kind of representing the sound wave. And if the source, which is creating a sound wave, let's say we have a source, sound source, is creating the sound wave. We know that the sound wave, the sound wave velocity is 340 meter per second, but the sound source velocity is increasing until it's become equal to the velocity of the sound. Yes? Let's say airplane. What exactly the airplane does? It does have velocity. Good. And its velocity sometimes is less than the velocity of the sound. you will see this. A. If the velocity of airplanes become exactly equal to the velocity of the sound, you will see this distribution of the wavelengths. But at one point, the velocity of the sound source become bigger than the velocity of the sound. Let's say the airplanes is moving with the 400 meter per second. What was the velocity of the sound? 340 something, yes?
It's breaking the sound barrier.
Exactly. It's breaking the sound barrier. But okay, what exactly happened? You will see these cones, okay? So if you connect these cones, okay, you will see this dash line. If you stand at any point in the dash line, you will hear a boom. Okay? So you will hear a boom, very loud sound. So that's why we call these wave bow waves. Okay, if you stand in this dash line location, okay, you would hear a boom sound. Okay, that's why we call it a sonic boom. So short wave, exactly, the same thing. Okay, I kind of explained. Okay, we are almost done. Okay, but we will, before moving to the next topics, I ask you to work on the example 1, okay? And in the next slide, you will see the solution. But try to work on this problem first. So, example, what is the frequency in hertz that correspond to each of the following period? So we have a 0.1, 5 second, 1.1 over 60 second. What you can do, you can grab a paper. When you grab a paper, okay, participate to this class with your cell phone first. Scan these, please. And join to the class again. You don't need to just join to the class with your real name. Join to the class. Okay. When you join to the class, start working on the first problem. What you do in a piece of paper, write your solution in a piece of paper, take a picture, and upload it here. You can take a picture, okay, solve this question, good, in a piece of paper, and then take a picture and then upload, because there is an upload. There is where that you can upload this picture. Okay. Okay. So let's review some of these. Okay. Thank you for participating. Let's start with this one. As you can see here, we know that the frequency is 1 over t, 1 over time period. What was the first time? Okay, 0.1. 1 divided by 0.1 is going to be 10 hertz. Good. The second one is 1 over 5. 5 second. Good. 5 second. 1 divided by 5 is going to be 0.2 hertz. Make sure to put the units. When you are calculating, put the units. Okay, 10 hertz, 0.2 hertz. And the last one, okay, is, what was how many seconds was the last one?
160.
160, yes, okay, which is going to be, there you go. 1 over 160 is going to be 60 hertz. Good. Yeah, 10 hertz, zero point 0.2, and then 60 hertz. What does it mean exactly? Again, hertz or frequency is the number of vibration over time period, or one vibration over time period. Formula: number of vibration over time, or one vibration over time period. Good. So we have a time period, 0.1, and then 5 and 1 over 60 second. You just plug into the formula and then calculate the. Good. Yes, I think, yeah, most of got the right answer. Perfect. Sounds great. Good. Yeah, I think everyone. Thank you. One more star. Okay, so let's move on to next problem. Do I need to show you? Okay, everyone know how. Okay, again, we are using this formula. F is equal 1 over T. Okay, 1 over, and the T, first just plug 0.1, then plug 5, then plug 1 over 6. Okay, so when we plug 0.1, is going to be 1 divided by 1.1, which is going to be 10 hertz. Don't forget the units. Good. So, which we have the solution here. Next one, again, you have 2 minutes. We will go over 2, 3 problem, okay? So, and then the rest examples you can just study by your own, okay, at home. We have a skipper on a boat. Notice wave. You can see this activity in your cell phone again. You just do the same thing. Wave crest passing his anchor chain every 5 seconds. He estimates the distance between the wave crest to be 15 meters. So the distance between two crests. So what does it mean? This is a wavelength. He also correctly estimates the speed of the wave. What is the speed? So we are supposed to calculate the speed of wave, yes? Okay, go ahead and just. I'm closing the submission. Okay, so thank you. Let's just choose one. Okay. Okay, we have speed is frequency time wavelength, yes? Frequency is 115 hertz, 1/5, yes? Time 15 is going to be, that's correct. That's correct. Yes, 3 hertz. 3 hertz. What does it mean, 3 hertz? So we are calculating the velocity. The velocity is going to be meter per second, not hertz. Good. So the unit of the velocity is meter per second. We are supposed to calculate the velocity. So again, 1/5 times 15. Okay, 3 meter per second. That's good. So yes, 3 meter per second speed is going to be the wave over time. Good. Yep. I think most, okay, they got the right answer. Okay, so, but if we want to solve, okay, so what is exactly the question says? It's telling that the distance between two crests, let's say if we have a wave like this, and these are the crests, good? The distance between these two is 15 meter. Good. So, and it's telling that a boat is here, and then how many seconds later it's meeting this second wave? 5 seconds later, yes? Make sense? So T is gonna be 5 seconds. What is the frequency? It's gonna be 1/5. Okay, so you can even calculate the frequency in this question. It's gonna be 0.2 hertz. So, and what is the wave frequency multiplied by lambda? What is the or lambda divided by t? It doesn't matter which one you are using. Okay, lambda is gonna be 15 meter, and the t is gonna be 5 second. So 15 divided by 5 is gonna be 3 meter per second, which most of you got the right answer. Okay, again, you can calculate the frequency and then use the velocity equal frequency multiplied by wavelength, or you can already have the period time, the time period, yes, okay, which is the 5 second, lambda over t. Lambda is the wavelength, t is the time period. 15 over 5 will give you the velocity of the wave. Okay, we will do the next problem as well. And then the rest you can do it by your own at home, okay? So because we have the solution and also the answer. Radio wave travel at the speed of light, 300,000 kilometer per second. What is the wavelength of the radio wave received at 100.1 megahertz on your FM radio? Yes, you have 2 minutes to complete this, okay, and then we will move on to the next. Okay, I'm closing if you haven't submitted, okay, so that's okay. But let's see what the question is asking us. Okay, radio wave travel at the speed of light. Okay, this is the speed of light that we have. Good. It's 300 kilometer per second. What is the wavelength of the radio wave if the frequency is, okay, so what information I have? I have wavelength, which is 300,000 kilometer per second. Okay. So, and then I have a frequency, good, it is 100.1 megahertz. Mega means million, okay? So mega means, it means that you just multiply this by 1 million, okay? 1 megahertz is 1 million hertz. So instead of 1 megahertz, I just plug, million hertz. Good. Now this is going to be my frequency. What else I need to do? I just need to, what was the wavelength formula? Let's see how many of you got the right answer. Did I close that? No. So 300, okay, 300,000 divided by 10, 100.1, okay, so 100.1 is better to convert it to the, again, hertz. Good. Because and second from hertz, they cancel each other, and your wavelength is going to be based on the kilometer. So we have 300,000, okay, so divided, so I cannot see. Good. 300 divided by 100 hertz. Okay, it is not 100 hertz, 100.1 megahertz. Again, you need to convert 100.1 megahertz to 100.1 time million hertz. Good. So yes, okay. When you do this, when you multiply this number, you will get the big number. So and then which is gonna be uh, in kilometer. Okay, but the way that we have solved here, I converted 300 thousands kilometer to 300 megahertz. You know how to use the unit conversion, but it doesn't matter. Let me, so you already have this. Okay, so let's say, let's do, my calculation. If we do this, if we assume that this one is nothing, okay, so it's gonna be 100 million. Good. So what is the wavelength? Okay, velocity over frequency. Yes. What is the velocity? Let me just use another color. Velocity is 300,000 kilometer per second divided by 100 million. Yep. Okay, how many zero we have on the top? We have 50, and then we cancel 50 from here. Yep. So what is left is going to be 3 kilometer divided by how many? 1,000. Good. We already know that the 3 kilometer is 3,000 meter. Yep. 3,000 meter divided by 1,000 is going to be 3 meter. The wavelength will be 3 meter. So next page, you have other unit conversion. Instead of converting the megahertz, okay, to a hertz, we just converted a kilometer, yes, to megameter. Good. So you have both. Okay. Good. Okay. The rest of the problem, okay, you can just do it by your own, okay, because the solution and answer is here. So we have 15 more minutes. Okay, so we just go over the rest of this unit. Okay, and then we are almost done. Okay, so sound, we just said that the sound need medium to travel. Good. So, and this medium is the air. Okay, so let's say you have, you see, we can create, if we have a tube like this, we can create a sound wave by a clicker. There is a clicker on the table, okay? So this Thursday you will do this experiment. You can create the sound wave. The sound wave, okay, reach to the end of this, yes, and then reflect it back. A standing wave. We will have a standing wave with the sound. But what happened here? We will have compression and rarefaction. So when we have this is a compression, when we have a constructive interference here, constructive interference, we will have a compression. These are the where we have a constructive interference, and in the middle, it is where we have destructive interference. Good. The reflected wave, okay, interfere with the incident wave, sound wave, and it's create the rarefaction and compression. So yeah, media that transmit sound. Okay, so there are media we can have. We have air. We have also a solid material like a table, like the water, like the steel. Okay, they all can transfer the sound wave. So the speed of the sound will change with the medium temperature. If the medium temperature, which is the air, change, the sound velocity will change. Let's say if we are in the cold room, the velocity of the sound wave will be smaller than when we are in the room with the higher temperature. Okay? Good. So the temperature of the medium, which is the air for the sound wave, if it changes, it will change the velocity of the sound wave. For instance, here, let's say the speed of the sound in dry A is 330 meter per second. So humidity and heat increase the speed of sound. For each degree, how much the speed of the sound increase? 0.6 degree. So if the speed of the sound in 0 degrees is 330 meter per second, if you increase the temperature by 20 degree, good? So for each increase in the temperature degree, what happened to the velocity of the sound? For each degree increase, we will have 0.6 meter per second increase on the velocity of sound. So at 0 degree is 330 meter per second. So what is at 20 degree then? How we can calculate? We can say 20 times how many? 0.6, yes? It's going to be how much? 12, good? At these 12 here, it's going to be 330 plus 12, it will be 342 meter per second. So each increase in the degree temperature will increase the velocity of the sound 0.6 meter per second. So reflection of the sound, okay, so we kind of explain what is the reflection of the sound. Let's say I'm talking in the class, how many walls we have? 1, 2, 3, 4. Okay, and how many objects we have? Many objects. Good. When I create the sound travels through the environment, okay, and reach to the blocks, any object, and the object reflected back the sound. And again, there will be a reverberation, constructive and destructive interference. If the room was empty, you would hear an echo sound. Yes? Let's say, you are moving to the new house. Nothing is inside the house. Good? So you will have a least reflection of the sound wave. What happened? Reverberation happened. Echo happened. You have heard the echo when you are talking in the room when there is nothing in the room or in the big hall. Yes? But when you fill the items, okay, so on the room, okay, on the living room, so what happened? We will have less, reverberation. So an echo is created by the reflection of the sound, okay, so and that's why we have a uh, acoustic in engineering. What they do, let's say we are in the concert hall, they would try to just uh, uh, increase the echo, or manage the echo which is created by sound wave, okay, inside the concert hall. So if you are interested, okay, there is another good topic for your term paper. So how acoustic engineering, okay, works in the concert hall or something like this. And we just talk about the refraction. Again, when the velocity of the sound wave change, we will have a refraction of the wave. What is the refraction? We already talked about the reflection. What is the reflection? The sound wave travel, or the wave travel reach to the block and then reflected back. But the refraction when the wave bends, When wave bends, when the atmosphere, okay, or the medium change its characteristic. So let's say the light or the sound wave is traveling through the air. Suddenly the air temperature at one area increase or decrease. When the sound see these change in the temperature, what exactly it does, because the velocity of the sound change, higher temperature, higher velocity, lower temperature, lower velocity. When the light or the sound wave traveling from a higher temperature to lower temperature, its velocity change. When its velocity change, what happened? The wave bends. It can be light wave or it can be sound wave. Good? For instance, here in this example, as you can see, we have a cold air and a warm air. The wave try to bend toward to the cold air. Yes? Okay, again, because its velocity is changing. The wave is try to moving toward to the cold air. Cool air. So energy, okay, so we will talk about the energy later, okay? So